Yeah, so let me share the screen. Uh, okay. Can I see my screen? You can see, right? Okay. So, till now, what we have learned is very basics how to start with our modeling. So every time when we talk about SACs, people used to think about only offshore structures. Okay. So maybe most of the time jacket structures. Then what people used to do is they will be designing the top side modules for FPSOs. So that is not even touching the sea, it will be on top of the FPSO. So some extra toe cases we need to consider. But when we there is some more things what we need to understand that is regarding the subsea structures. Now let's say let's say this is our sea level. So can you see my screen or do I need to share again? No. Okay. 1 minute. I think. Yeah. Minute. Just hold on. Sc- Okay. Uh, can you see my screen?
Yes.
Okay. So here, so let's say this is our sea level. So in the sea level, we will be having jacket structures. So there will be offshore jackets. Will be here. We have topside modules. Sometimes we may have a FPSO running over here, and there will be lot of topside modules for the processing and all. So, but what happens with both these structures is they have something at the bottom of the sea. So, if you look here, there will be pipelines flowing and it will be coming to a section. So, there may be lot of subsea structures. So, what we call this pipeline end termination. Um, so there is plumb. Then what happens is from all these things, pipeline will go and we will come to something called manifold. So we will come to something called manifold. From manifold, there are a lot of distributions going to different wells. Okay. And for each well, on each top of the well, there will be something called Xmas tree. So we call it Xmas trees. So it will be on top of the wellhead. And from each well, this manifold will collect the oil and it will be taking over. So when we talk about the matmat structures, there are something in common with them. So usually they will have a foundation. Usually they will have a foundation like this. In this foundation, what happens is the foundation will make sure that the structure will stay intact in that location. So most of the time it will be called mat. So mats will be like plates with perforations. So there will be holes on the mat, and so these are just plates. So to strengthen the plates, we will provide beams. So these are beams. So there will be beams on the outside. So this one will make sure our structure will not get penetrated because the soil is very loose. So it should stay over there. So it will not get penetrated deep into the seabed. But the structure needs to stay. That's why we provide a mat for stability. Then there is top structure. So on the top of the foundation, there will be top structure. So this top structure will have different functions according to what is the type of structure. So if it's a manifold, it should collect oil from different regions, collect it and send it to another module. So it have its own function. There will be a lot of pipings, everything involved. So pipings is not part of our scope because that is with piping engineers. So they may be using some software called autopipe to model that. But as a structural engineer, we need to make sure this structure is intact and it is structurally stable. And there is one more component when we talk about this magma structure. There is something called a skid. So, so we call skirt plate. So it is called skirt plate. So it will ensure that this skirt plate. So these are just plates. So this will ensure that okay, our structure will penetrate deep into the seabed. So that will make sure that if the currents pass on the structure will not be swept over. The structure will not be swept over, and it will make sure that the structure will stay in place during any of the external load acting on it. So as a structural engineer, what we need to do is we need to make sure that okay, the structure we design is good and it can take all the load cases required. So when we come to the load cases required, there are few cases which we used to design. So first one, the critical one is the lifting case. So lifting is the most critical one. So when we do the lifting analysis, always make sure you do the skew analysis. I will explain to you what is lifting and skew. Then what we need to do is we need to do a transportation analysis. Transportation analysis. Then what we need to do is an in-place analysis. So transportation is like when we take the structure from a certain location to the field, this transportation will be critical. So there are road transportation as well, but when we compare to the sea transporters, that will be very critical. So we will be dealing with the sea transportation. Then in place means we will take the structure, we will go to the seabed. So in the seabed, what are the external loads that can act on the structure? So here, most of the time, it will be just due to water depth and some currents may be coming because waves to that deep, it won't be affected because it will be very deep. That also, but we have certain external loads coming into it. That is very critical in the in-place analysis for subsea structures. So, because there are a lot of pipelines coming and attaching to it, each pipeline will exerting some sort of load. So we need to create a load combination of these. So that's how the in-place will become a little bit relevant with respect to the loads. Then the another analysis what we need to do is the recovery analysis. Recovery analysis. So when we tell about recovery analysis, why we need to have a recovery analysis? Because as per international protocol, once the lifetime of the structure ends, we cannot just abandon the structure over there. We need to retrieve it from the seabed. We need to retrieve it and bring it back. So we need to do a recovery analysis as well. So we will be doing these four analysis. So what we will be going to do is we will model one MATMAT structure. So the structure what we are going to model is a wet parking frame. So that will be uh, that will have the basics of everything, and it will be easy for to understand as well. Before coming to wet parking frame, let's talk something about the lifting cases. So, have you done lifting analysis in your projects? Hello.
Lifting analysis, no. Just
Okay.
review the lifting drawings.
Okay. What about Anagraha, Anandan, and Mohan?
I did, but not in that much detail, sir.
No, sir. No,
Okay.
I haven't
So,
done that.
Yeah, okay. So when we talk about lifting analysis, we have few critical cases. Okay. So what happens is, let's say our structure weight is like 1 ton. When we do the lifting analysis, we will be applying some extra factors to it. So let's understand what are the factors involved into the lifting analysis. So what I am going to follow is TNV STN001. So this is the latest version. Earlier it was DNVGL STN001. I have a old copy. After today's class, I will share it with you. It will be almost relevant, but only few changes with the latest version. If you have the latest version, you can follow that. So we will be using few factors extra on top of the weight. Let's understand what are these factors. First one is weight contingency factor. So this one people used to call in different names. So first one is weight contingency factor, or people used to call it weight growth factor. Weight growth factor. So this factor is like so when we design any structure, we have different stages of design. So first one is called feed. So feed is called front end engineering design. Front end engineering design. So this is the initial level before the awarding the contract. So this is the initial level of analysis we used to do. So to check the feasibility and all. So this won't be that accurate. We will take some not to exceed loads. So we will be having some historical data. We will take some not to exceed loads. We will do for some critical cases, and we will check whether this arrangement or this structure or this methodology is going to work. Sorry, my screen. Okay, it came back. So that is feed stage. Then another one is detailed engineering. So once we have this EPCI, engineering, procurement, construction and installation stage. So what we have feed first, then once the award is contracted, it will come to the EPCA stage. So in the during the EPCA stage, first we will have a detailed engineering phase. So here we got the award, we got the contract, and we are going to start the engineering of the structure. So here we will be very detailed, but still we are not sure regarding what configuration we may achieve, because we need to do lot of iterations. We need to check for everything. We need to optimize the weights. So once we were working for a project for total, we were designing a wet parking frame. We went for almost 40 iterations to bring in stick on with the final version of model. So here we need to do a lot of iterations. So this is called a detail engineering phase. And once everything is ready, so first usually have once we have the detail engineering phase, how things will go is we will do all the internal engineering checks, and we will have some design reviews. We will call it design reviews, DRs. Then we will have checks, internal checks. So after internal checks, we will send it for revision, IFR. We will send it for revision to the client. So this will be to the client. So once client gives their comments, so they will give the comment. We need to incorporate the comment, and we will issued for AFC version or IFU version. Different companies use different names. So AFC is called approved for construction. IFU is called issued for construction, or last some people used to call IFA, issued for approval. Different terminologies with different companies, but this is the process. So in the detailed engineering, let's say I will call it I like IFR stage, and once we finish the detailed engineering, we will reach the AFC stage, approved for construction stage. So these are three stages, mainly three stages. In that, it can again go very detailed. Okay, So during these stages, here we have lot of uncertainty. Here I am very much uncertain. Here little bit uncertain. Here I am less uncertain. So so this weight contingency factor, as a general case in a practice, what we used to consider is 10%. That means, let's say, if my weight is 1 ton, I will consider an extra 10%. That means I will consider a factor of 1.1. That means I am going to consider just the weight component instead of 1 ton, 1.1 tons. So that is the concept behind 10%. So, but during the design stages, this value can vary. So, for total, what they are specifying is, for feed stage, consider 1.2. For detailed engineering stage, consider 1.1. And for AFC stage, you can bring it down to 1.05. So this one varies with different clients, but we need to go as per the client specification. So is weight contingency factor thing clear with you, all of you?
Yes.
Yeah, yeah.
Yes.
Okay. So that is a weight contingency factor. Then there is something called a dynamic amplification factor. This is a little bit critical. Okay. So dynamic amplification factor, it is like when we do the lift, that is not a static lift, because the vessel will be moving, winds will be coming onto it. So it will have some dynamic effect on our structure. Okay. But what we are going to do is a static lift. So we need to account for how much dynamic effect will be happening. So this effect, so this DAF value will define uh, where it occurred. Okay, this DAF value will define where it occurred. Now let's say I am lifting it. So if you look over the field layout, how it looks like is, let's say this is my port. So port, I will have very calm waters. If the crane is in land, it will be very calm because it is not in motion. So have you visited any ports? Most of you may have, I think. The ports will be very calm because it have breakwaters. So breakwaters is just a wall of rocks. We keep it so that when the waves come into the port, the waves will not get inside. So the water will be very calm. Okay. So this is very calm over here. So when we used to lift it in the port, we can select a factor of 1.1. Now let's say we keep it on the vessel. This is our vessel. Now we are taking the vessel and going to the sea. So in the sea, what happens is there are waves. So the dynamic effect will increase. Okay. Dynamic effect will increase. Now I will draw another schematic. So this is wave part, and this is my ship. So my ship is over here. This is my crane of the ship. Okay. So I am lifting something. So now this one is in air. Okay. This is in air. Only wind and vessel motions will be there. So this, at this point of time, the DAF value will be approximately 1.3. So 1.3 is the approximate DAF value. But if it's very a rough sea like North Sea and all, I think they used to take 1.5. But generally we can go for 1.3 or 1.5. That is when we are at the sea. At the air, our cargo is in air. But what happens for the subsea structure? We need to bring the structure to the seabed. When we bring the structure to the seabed, we have a problem. We need to cross this area. We need to cross this area. This is called, this particular area is called splash zone. We call it splash zone. Splash zone area is very critical because you just imagine the waves will be hitting on it. This is very critical part. It will be inducing lot of movement or on the structure. So at this point, the splash zone value, the DAF value, the installation engineering teams used to take it 1.9, but in my company, structural engineering teams will directly take conservative DAF value of 2.2. Again, you can refer to the client specs, what DAF they are preferring at this area, but this is the average we take for this particular region. So here, just imagine it's a sea, waves are coming and hitting. So this guy will be moving like anything. So to reduce this depth, what we installation engineering team used to do is they will increase the weight of the structure. So when that I will come into discuss. Just remember weight, how weight is acting. Just remember that we will be discussing it now. This splash zone value, the DAF is critical. So when we do the lifting analysis for subsea structures, we directly take the highest DAF. Okay, if we do it for highest DAF, that will be taken care of. So that is the DAF value. So DAF value, let's say I am going to take 2.0. Is DAF clear with you? Hello.
Yes, sir.
Okay. So now we understand DAF. Next one is called the um, consequence factor. So this is a very funny factor, consequence factor. So consequence factor, we call it short form CF. So the concept of consequence factor is, let's say I'm going to draw a plan view. Okay. So this is my structure. This is my plan view. I have beams running over here and here, let's say. So to lift the structure, we may have something called paradise or lifting points. Have you heard about paradise?
Yeah, lifting leg.
Yes.
Yeah. So paradise will have a form like this. So paradise will be having it will be a plate structure, and we will be connecting shackles to it. We will be connecting shackles to it, and we will be lifting. So the concept of consequence factor is something can go wrong and fail the structure. Okay, something can go wrong and fail the structure. So we need to make sure that this doesn't fail like that. So that is the thing. We are putting some extra factor to make sure that this doesn't go, it's not going to fail. And even in the consequence factor, there is some recommendations. So which all structures, so let's say which all structures are directly connected to a paradigm. So these three members are directly connected to a paradigm. This is directly connected to a paradigm. Similarly, these three directly connected to a paradigm. So all the members which are connected to a lifting point, we will consider a consequence factor of 1.3. And all other members a consequence factor of 1.15. This is as per DNVST N001. Okay, so this is the idea behind it. So we are just making sure, okay, this doesn't get failed. So it's some sort of extra assurance. So what we usually do is because to split the factors here differently, that is a very tiring process. And in Subsea, we don't care much about the extra weight on the member unless it doesn't fails. So what we do is we will directly go for 1.3 in that case. So what I will do, I will come over here and I will select 1.3. So consequence factor clear?
Yes.
Okay. Next one, So there are two more factors which we usually use for. So all the lifting what I have done is with the single point, single hook point. Okay. So the other one, what we used to do, there are two factors extra. One is COG shift factor, and another one is Q factor. Before going to skew factor, let's discuss COG shift factor. So now let's say this was my plan view, and I am going to connect the sling. So how there will be a hook point, and I will have slings going from that hook point. So now let's say this my COG is a geometric center, and we will always make sure the hook point correctly matches with the weight COG, not the geometric COG. So whatever be the final weight. So if everything is uniform or what we say, symmetric, uh, the actual COG, weight COG will match with the geometric COG. But now let's say we have a weight over here. What happens is the weight COG will shift over here. Then what we do, we used to connect the slings to that hook point. Okay. So this COG location matters a lot. So if our hook point is not at COG, because we always try to make sure our structure stay flat, unless otherwise it is intended. So sometimes they will exactly tell, I want to lift my structure in an inclined position. So let's say in an ideal case, we will make sure our structure is horizontally in level. But some cases they will intentionally tell, I want to lift the structure in an inclined position. So in that case, we can go for inclined. So now what happens is, if we when we select the rigging everything, we are taking it from the COG location and hook height. Now, if my COG shifts, there will be some imbalance from what I estimated. So let's say if my COG shifts over here, there will be imbalance on these slings and some failure can occur. To avoid that, we used to consider a COG shift factor. So this COG shift factor, the general value is 1.05, but some clients will ask us to actually simulate a COG shift. Then what happens is, let's say this is my, sorry, today I am more focusing on theory part, so that I thought it would be better if you will be able to understand what we are doing rather than directly do. Is it okay with you?
Okay,
Yeah.
no issue.
Very, very much.
Okay, okay, okay. So let's say this is my structure. Now this is my COG location. So let's say this is of length L and this is of breadth B. Okay. So what some companies will tell you that your COG envelope can come anywhere between 5% or 10% of the actual dimension. So let's say we will go for 10%. So what it indicates is, let's say this is our COG. Let me draw a central. So if I consider 10% of it, that is 0.1 times L and zero point 0.1 times P, if I consider this as a rectangle and with my current COG at the centroid. So it will be something like this. So this is 0.1 times L and this is 0.1 times P. So this indicates that my COG can come anywhere in between this envelope. So that is the that is the extra contingency what I am going to consider with the COG shift. So they will ask us to actually simulate this case. So here what we will do is, in this particular case, we can go for the extreme corners. So these extreme corners will be the case that then we need to do 4 cases with hook points coming to these corners. So that anyway we will do, but just understand there is something like this COG shift. Did you understand what I intended with this envelope thing?
Yeah. The COG can come
Yeah.
anywhere in that boundary, so it's still acceptable.
Yeah. So if so still acceptable, that's a different case. That will only so what happens is, once they fabricate everything, they will do a trial check and the COG match. So once they fabricate it and they do it, if they want to say it is acceptable, means we need to do this COG lifting case within this envelope. Now let's say when they fabricate, the COG comes outside, that means we again need to do this analysis considering, okay, COG came over here. So what happens if I put sling over here? Okay, but to tell them that anywhere in this envelope is okay, that means we need to do this particular analysis. Okay, so that is the idea behind it. Now, so this factor now, for as of now, let's keep it as 1.05, and we will do the actual COG shift once we finish the first lifting cases. Next one is the very important factor. So during some interviews also this question can come. Skew. Skew is what I would say very critical, and most of the people used to interpret in a wrong way. Have you heard about skew?
No.
Okay, so to understand it, it's simple. If you understand the concept, the thing is very simple. So the thing is, let's say, let me draw this one again. So this is my plan view of the structure. And I have lifting points, 4 lifting points. Okay. So I have 4 lifting points. Now, if I want to connect these lifting points, what I usually do, in if you have seen some installation operation, what they do is they have something called soft sling rigging. So they call it soft sling rigging or web slings. So in that cases, even for but for wire sling, what happens is they will have a master link. From the master link, they will have sub links and they will be connecting the wire rope. But still, we will consider this case because we consider everything as a single side take. Now, even for the soft sling or web sling, what they do is soft sling, no, web sling. What they do is we will assume, okay, no, we will connect. So we will take one sling. So if we take one sling, we have 2 ends. Each end we will connect one shackle, here another one shackle. And now what I will do is, I will connect one sling like this from this pad eye to diagonally opposite pad eye. Similarly, another sling from this pad eye to another diagonally opposite pad eye. Now what I do is I can take a hook point, connect it here. I can take a hook point, connect it here and lift. So this is the general concept when we use this web slings and all. But for skew easy understanding, this concept is. Are you okay till here? Till here, are you okay?
Yes.
Yeah.
Okay. Now consider that our actual weight COG is matching with the geometric COG. I don't have any changes. It's matching. Now, my total weight is 100 tons. Let's say my total weight is 100 tons. Now, if I go for equal distribution, in ideal case, so this sling, everything capacity is same. In ideal case, what happens is this pad I should take 25 tons. This one should take 25 tons. This one should take 25 tons. This one should take 25 tons. Are you okay till here? Equal distribution, right? So that means this particular sling will take total 50 tons. Because the incline tension will be varying, that's okay. But totally, it should take 50 tons. This one will also take 50 tons here and here. Now, so these are all our conception was equal length, everything. Now just consider due to some fabrication tolerance issue, there was some fabrication issue. Our one of the slings becomes slightly lengthy. Slightly, it won't be that much. It will be little bit small only, slightly lengthy. When you connect, you didn't feel the difference overall, but it's slightly lengthy. Now what happens when I start loading? When I start loading, what happens is, which one was shorter, it will get loaded first. In the earlier case, when the length was equal, both should have take loaded first. Now, when if you are looking from the side view, what you will see is our structure is like this. This is pad eye locations. Sling is lying at the base. We are connecting the hook. Now we are slowly lifting the hook. So now it is coming upward. Now, once it is coming upward, the shorter one, first it will be showing the resistance. The shorter one will be showing the resistance. It is started to get load, and slowly, once it start getting load, and it start elongates, and when it reaches the length of the other one, then only the other one also start taking the load. Do you agree to my statement?
Yeah. This is because of the pad eye location is wrong, or the sling is
No.
incorrect length of the sling.
So here the main consideration what we gave is incorrect length of the sling. That is due to fabricational mistakes, not due to anything. Because if we select a wrong length, that is a different mistake altogether. But here we are considering the ideal case. If we bought two slings, but something due to fabricational mistake, one sling was extra in length. That's why this initial load mismatch happened. So once it goes like that, there will be some sort of load mismatch. So instead of this 50-50%, so this was 50%, this was 50%. The shorter one will take more, 50 plus X, and the longer one will take 50 minus X%. This is 50 plus X and 50 minus X. So let's understand our ideal case, it should be 50-50. Okay. Now, due to fabrication tolerance, Q happened. So what happens? One thing will take 50 plus X percentage extra. So this is in percent. It's in percent. Another one will go for 50 minus X. So if you sum, it will be 100. Okay. Now, skew factor definition is this 50 plus X by 50. That is the skew factor definition. Did you understand this definition? Do I want to tell any again? Maybe I will tell again. Just
Yeah.
this, So initially, our one sling and the other sling both were same length. So the total weight distribution between this sling and this sling was 50-50%. Are you clear till here? 50 is correct, right?
Yeah.
Okay. Now we have a load distribution happening due to the increase in length. So one is taking more load and another one is taking less load. Okay. And this will result in a unequal split. Instead of 50-50, one set of sling will take 50 plus X%. So if this was, so total is 100%. So if one increase happened, a corresponding decrease will happen in the other sling as well, right?
Yes.
So this is clear. So
Yes,
ah,
sir.
so ah, so this increase divided by the ideal case. That means that 50 plus X divided by 50. That is the SKF value or skew factor value. Now is it clear?
Yeah.
Okay. Now the important thing. So people, so as per DNV STN 001, what it recommends is we need to consider a skew factor of 1.25. Okay. We need to consider skew factor of 1.25. But for heavy lifts, for jacket topsides, and even for some total related thing, what I have seen is they consider a skew factor of 1.5. So now let's say if I go for a skew factor of 1.5, what will be my increase in percentage? That means 50 plus X by 50 is equal to 1.5. That means 50 plus X is equal to 50 into 1.5, that is 75. So X is 25%. Okay. That means when we consider a skew factor of 1.5, the split what we will get is one set of slings will take 75% and another set of sling will take 25% of total load. Are you clear?
Yeah. If there is an asymmetric structure, so there will be this Q factor applicable, or
So asymmetric. Okay. So see, whenever we have this 4-point lifts, skew factor will be applicable. We need to do skew. That is very important. If we don't do skew, that means we are missing. And if we don't skew and we perform the analysis, lifting everything, and now we are sending it to some societies for verification. So usually client, what they will do is they will send it to DNV or some LOC, London Offshore Consultants, or a PV. So they will verify our design reports. So they will definitely catch you didn't consider the skew. So what people used to do the mistake is they will directly apply the factor on top of the total lifting factor. That is the wrong approach. Don't do that. I will show you how to do in two different ways. So this is regarding 1.5. Now for 1.25, how things will go? It will be 50 plus X by 50 is equal to 1.25. So 50 into 1.25. So it will come to, let me take the calculator. I think 62.5. Calculator 50 into 1.25. 62.5. So this one will be 62.5%. That means the X difference is 12.5%. So if you look at the lift split for this one is 62.5% and 37.5%. This is the split for 1.25 This is a split for 1.5. So this one's still clear, right?
Yes. Yeah.
Yes. Okay. So now if I come back, what I will have is skew factor. Let's say I go for 1.5. Now, if I want to calculate my total lifting factor, it will be like 1 point what into that's weight growth factor. Then DAF 2.0 into 1.3 into 1.05 for COG and 1.5 for skew. How much do you will get? 1 minute. Let me do the math. 1.1 into 2 into 1.3 into 1.05 into 1.5. So this will be like 4.5 times. So it will be like 4 times the total load will come. But this is the primary estimation. But what we will do is we will actually simulate the skew. We will actually model the lifting such that it will take two different loads. So in that case, we can cut this one. Then we can do the actual COG simulation as well. So in that case, we can cut this one. Then what this one will come? This one will come to 1.1 into 2 into 1.3. So it will be like 2.86. So this is the average value. So according to different client specs, it can increase or decrease. But this is how you considered the factors for a lifting calculation. Now, once we model it, there are few more things you should be remembering. So let's say,
What
yeah,
is the value we get total? What we can call collectively for this total means you divide all the factors and
no.
there is.
So so we multiply these factors, no? So
Yeah.
we are multiplying these factors. So we will get a final factor. So what we do is when we do the lifting analysis, so let's say this is our cargo, this is my sling. So if the actual weight was 100 ton, I will multiply it with 4.5 times. And then I will do the lifting analysis. That means I'm going for very conservative part. I'm going for very conservative stage. And I will do the analysis. I will make sure my structure doesn't fail. Okay, that is the concept behind that. Now coming to the modeling of this one, there are few things we need to consider. So first one is regarding the modeling of the hook point and sling. So let's say this is my structure and this is my lifting points and this is my hook point. So when I draw this sling, one normal consideration is this angle which sling makes with the horizontal. So it will be in plane of that sling. So when I draw from side, I can just show it like that. That angle should be minimum angle, minimum 60 degree. Okay. This angle should be minimum 60 degree. Why 60 degree is important? Because there will be some tension coming onto it. So it will have a component. So let's say this is theta. It will have a sine theta component and it will have a cos theta component. Okay. So how the cos theta value changes from 0 to 90? So cos 0 is equal to 1 and cos 90 is equal to 0. But for sine 0 is equal to 0 and sine 90 is equal to 1. That means how much we increase this, our vertical component will increase accordingly, this angle. Okay. So how much we increase this angle, our vertical component will increase accordingly. That means with a less tension, we can achieve more vertical component if we have a higher angle. That is one concept. Then second one is, if we reduce this angle, that means whenever this angle reduces from 90 to 0, what happens is the horizontal component will increase, cos value will increase. What happens? The cos component will increase. It will insert a compression load between these numbers, which may result in a buckling case. Did you get it? These 2 points? Cos, sine and cos happening? Hello.
Yeah.
Okay. So just understand we have two components. Then you may ask, why stick on to 60? Why you can go till 80 or 90? Because we have some constraint called height constraint for the crane. So if you see the crane, usually crane what happens is, let's say this is the tower and this is the hand. So if you look at the capacity chart, and we have some constraint regarding the height. So if you look at the capacity chart of a crane, what happens is, towards the radius, the capacity will be higher. And when we go outside, when we lift the hand, the capacity reduces. The capacity curve usually show like this. This is higher capacity, this is radius. Okay. Now we have certain limitation regarding the height of the hook. So we need to make sure our enough hook height will be there. Okay, we cannot just increase just like that. So people used to say, okay, minimum is 60. Whether I can keep on increasing. No. We need to check with the installation team to make sure, okay, if there is any constraint regarding the hook height, do I have a limitation? What is the minimum hook height I can use? You should use upon it. But in certain cases, let's say if you have this angle is very low, it's very low. In that case, you can consider adding some frame or something extra to take care of this one. That is a different topic altogether. But these are the major consideration while doing the lifting analysis. While modeling in SACs, there is one more consideration. So usually what happens is, when we model a sling and the object, it will show some rigid body movement. So this rigid body, because SACs is based on some equation, that FEA equation. And if a rigid body movement comes, that equation will not get solved. So that we need to arrest this rigid body movement. So as a general case, what we used to do is, it's a practice. I never seen somewhere actually written, but this is the common industrial practice to provide weak springs. So we will provide weak springs at the bottommost corner. Now, if I look the plan view, there are two approaches of providing the weak spring. So weak spring, what we used to provide is 10 kilonewton per meter stiffness. Springs we will give over here. So this one we will give in X and Y axis. X and Y axis at two corners. That will be enough. But I have seen another approach as well. So at this corner, it will give only for X component. This corner, it will give only for Y component. And at this corner, it will give both for X and Y components. This is another approach. I have seen and I have used two approaches. Anything is fine. What I would suggest is, the most common one, what I found is this one. I would ask you to follow this practice. So once we set up the model, you will understand this part. Okay. So this is how the things what we do with the lifting analysis. So in the next class, what I would do is, we will model a mathematical structure, very simple one. a wet parking frame, and we will do lifting analysis. So we will what all things we will do is we will do a normal lifting analysis, then we will do a skew lifting. So normal, skew, and what we will do is skew plus COG shift. So we will do all analysis. Another one more important thing I need to tell you. So all these factors which I told you is based on DNVST N001. But for API-RP, it doesn't explain all these factors. It only give two cases. First case, less critical one, go for a factor of 1.3. For highly critical one, go for a factor of 2.0. That's it. Only these two factors API specifies for.
So if we are following API, then this consequence factor DAF
No, no,
is
no, no.
these values where we will.
You don't want to consider any of these values till skew. Skew, we will actually model. Even if we are using API, we will actually model the skew of 1.5. But these things you can ignore. You can just use the API one.
So it is
So
not
that
that
will
much important, or
no, that's the problem. So API is very, I would say, less conservative when coming to the lifting. And for other checks, API is very good, like pipe check and all. But for the lifting, APA doesn't consider much about it. But when we come to DNV, this because API most of the time deals with bigger structures. That's why their factors all are less. Because whenever we have a bigger structure, when the weight increases, dynamic amplification thing also reduces. Okay, that you can just imagine. You suspend something from with a rope downward. Now see let's say you suspend a normal balloon. During when the wind comes, the balloon will move in a very rigorous way. Now if you suspend a football, it won't move that much, right? That means the weight, when the weight increases, things get more stable. That's what so I if the DAF is more, and if we are not able to do that installation, what people used to do is they used to add some extra weight called clump weight. So they will add clump weights, and in the clump weights, what it will do, it will add some extra weight to make sure that okay, structure doesn't behave violently, and the dynamic amplification factor value will come down. So in that case, we can reduce. That's the justification what I got when I checked with the API and DNV. But DNV go for very DNVST and 001 go for very wide range. So when we compare the weight of a jacket and when we compare the weight of a subsea structure, subsea structure weight is very less. So there all these factors matter much. But for the bigger structures, it doesn't matter that much. Yes, we are considering some extra factors, but not to that extent. That's the idea behind it. So today I will stop over here. I will send you the recordings. Go through the recordings. If you have some doubts, you can ask me, or you can have a normal Wikipedia search. Will give you a lot of idea. Okay. And test we will have. We will start the modeling part. Okay. All clear? All good?
yeah. Last one thing, this in-place analysis means what is the concept?
See, in-place analysis is nothing but we design the structure to go to perform some function at some location. Now we are considering, okay, our structure is going to that location. Now the structure is in that location and it is doing that particular function which it was designed for. Now what all loads will be coming into it? That is called in-place analysis.
You mean the wind, everything?
See, wind will come for structures which are exposed to the wind. Now, if you look at the jacket, some part of the jacket is above sea level, some part of the jacket is below sea level, some are at the mean sea level. So for a jacket is a very classic example to consider all the environmental loads, because waves will be there because some part of structure is at sea level. Mean sea level only, that wave effect will be there closer to that. Wind will be there because the structure is exposed to the sky at the top. Current will be there because structure is till the seabed. So current definitely will be there. But if you take the subsea structure, it's deep under the water, no wave or no wind. Most of the major part is current only. But here, even the current is also less at some locations. So at that time, because the structure, the exposed regions will be less, so current may be less. So what we usually do is we will consider what are the extra loads coming into play when we have some issue with the soil stiffness and all, because soil will be loose. If we are putting it on the land we will consider it as a rigid surface. But soil, it will be like movement. So we need to get a soil stiffness. We need to convert the soil stiffness to different locations. That all we will be doing in the in-place analysis.
Okay, okay. Thank you, sir.
Okay, clear, right?
Yeah, yeah.
Okay, then. Then we will stop over here. I will send you the recording, and we will meet again on Thursday. Okay.
Okay.
Okay. Good night.
Okay.
Okay, thank you.
Good night. Good night. Thank you.